Now, I would like to talk about colloids rather than solutions and the difference between them. So, a colloid is going to be, colloids are going to be dispersions rather than solutions. They're actually heterogeneous mixtures rather than homogeneous because um, the particle size is large enough that we can start to consider it to be a separate phase than the solvent. Um, but the trick with these ones is we can't actually separate them if we leave them alone, like just letting them settle. Like if we let it sand, we won't see it separate. So our solutions won't separate at all, right? They're these homogeneous mixtures. So we have solutions kind of on one spectrum. And on the other end of the spectrums, we have suspensions. This is like the snow globe in the chemistry world, right? A suspension is when you're going to be able to see that the mixture isn't actually a homogeneous solution and you can see particles and they're suspended in the liquid, right? Like a snow globe. Or I don't have another great example. And so colloids fall in the middle. Colloids are this kind of range where the particle size is so small, it really looks like a solution, but it's actually just large enough that it's not going to behave as a solution. So, our particle size for colloids is very specifically between 1 nanometer and 1,000 nanometers. Larger than 1,000 nanometers, you have a suspension. Less than a nanometer, you have a solution. And so these particles are going to be able to coagulate with one another or aggregate up and kind of make larger particles than that. And so we see that colloids won't actually be able to pass through a semipermeable membrane at all. So we see that our colloid won't be able to pass through a semipermeable membrane. Now, these particles are going to move around according to Brownian motion. So they will be going in random directions and colliding with other particles as well in this liquid. And you'll be able to tell it's a colloid because it'll exhibit the Tyndall effect. Tyndall effect is when is when it scatters light from the colloid dispersion. And so when you shine light through the solution, typically like a solution, you don't actually see a beam of light. But that Tyndall effect is you see that beam of light as it passes through the solution, and it's kind of dispersed, scattered by the colloid itself, creating this really cool effect. So we aren't going to do any calculations with colloids. I'd just like you to be able to recognize the difference between solutions, colloids, and suspensions. And colloids are clearly the best of these because it's ice cream. So here's my favorite colloid, ice cream. And it's got air bubbles and ice crystals and fat globule fat. Um, and some of these kind of aggregate together and they kind of coalesce together. And the particle size is so small that we actually have a colloid here. So another colloid to look at is the micelles created with soap, and it'll create a colloid suspension when it's added to water. So a soap particle is going to have a hydrophobic tail and a hydrophilic head on it that has a negative charge, which is key. So it's got a dipole moment with it. It's got a negative charge and it has this long nonpolar tail. And so it'll form these micelles, micelles in solution where the nonpolar tails all kind of come together with the polar heads outside the micelle on the outside facing and interacting with the water. So that way our hydrophobic tails are interacting with other hydrophobic tails rather than having to interact with water, which would have drastically different intermolecular forces because that tail doesn't have any hydrogen bonding capabilities. And so these micelles form and they form a colloid in water and they can come up to a greasy particle and surround it. And that greasy particle would be soluble in the hydrophobic inner core of the micelle. And the outer part of the micelle would be able, the polar part, would be able to interact with water and get flushed and washed away. So soap's pretty amazing.